Hello everyone, I am G. Shankar Varma, Assistant Professor of EC Department, Marri Laxman Reddy Institute of Technology and Management. Today I am going to explain about DC characteristics of op-amp. That is my second lecture on the subject called Integrated Circuit Applications. So in this session, we are going to discuss mainly about the basic concepts of op-amp, IC741 op-amp and its features, comparison between ideal and practical op-amp, DC characteristics of op-amp. Actually, these course objectives, course outcomes, syllabus, basic concepts and op-amp features we already discussed, but I just want to revise about these two topics, basic concepts of op-amp and IC741 op-amp and its features. After that, we will see these two new topics, that is comparison between ideal and practical op-amp, DC characteristics of op-amp. So these are the course objectives, course outcomes and course syllabus. So in the syllabus, first unit integrated circuits and operational amplifier, we have already covered introduction, classification of ICs. In the classification of ICs, chip size and circuit complexity is one of the type. Apart from that, basic concepts of op-amp IC741 till now here I have completed in lecture 1. But just I want to revise only this concept, basic concepts of op-amp. After that, we will see ideal op-amp, that means ideal op-amp versus practical op-amp as well, and op-amp DC characteristics. This we will see, these two topics we will see in this lecture, that is lecture 2. These are the textbooks and references required for this subject. So coming to the basic concepts of op-amp, in the last session itself, I have given small introduction regarding this operational amplifier. This is an analog electronic device which takes analog signal as input, and after processing, it will generate analog output only. If we observe this symbol of operational amplifier, it is having two input pins. These two are the input pins. One is non-inverting terminal. We call it as non-inverting terminal or non-inverting pin. Second one is inverting terminal. Non-inverting terminal, we will represent it with positive sign, and inverting terminal with negative sign. And two more important pins will be there, that is power supply pins. Those we call it as V plus and V minus. Those two are the dual supply pins. And the last one is the output pin. So after processing the signal, the operational amplifier will generate the output across this pin only. And this diagram represents the pin diagram of op-amp. If you observe this pin diagram of op-amp, total there are 8 pins. So these kind of structures, generally these kind of ICs are called as dual inline packages. DIP, simply we call it as DIP or dual inline package. Dual inline package means, if you observe in this IC, left side 4 number of inputs are there. Right side 4 number of outputs are there, or 4 number of terminals are there. So both sides the pin count should be same. That is called dual inline package, and it has to follow that standard. So we'll see one by one pin. So if you observe first pin and the fifth pin, both are called offset null pins. So before going to explain about this offset null pin, first we have to know what is the term offset. Offset means consider any electronic device apart from oscillator. So apart from oscillator, if you consider any electronic device, simply if we without giving any input, like one electronic device is there, without giving any input, if input is 0 or we are not giving any input, then the output should be 0. So apart from 0, if we get any positive value or negative value, it means the electronic device is generating some error or some unwanted signal. Simply we call it as noise. So that noise is called offset value. I will repeat again. Consider an electronic device. We are not applying any input, or we are applying 0 input. Even though it is generating some output value, that particular output value is called offset value. So we have to make that offset values as zeros. Now consider pin 1 and pin 5. Here how can we reduce that offset values? How can we make that offset values as 0? That is the concept offset null. Null means 0, right? So first of all, we have to measure what is the offset value. Okay, we have measured and we got some value. Now we have to adjust a potentiometer, adjust the pot or potentiometer in such a way that the offset value will become 0. So we will connect. Potentiometer is nothing but variable resistor only. So here I have connected a potentiometer across pin 1 and pin 5. By keep on varying it, we can make the offset values as 0. Okay, that is the purpose of pin 1 and pin 5. Coming to second pin, as we have seen in the last slide, inverting input. Third pin is non-inverting input. If you observe this symbol, we are having two input pins now, inverting and non-inverting. Those two pins are here. Next, coming to pin 4 and pin 7, as we have seen in this symbol, there are two supplies. We call it as generally dual supply, V plus and V minus. Those two pins are 4th pin and 7th pin. Coming to the 6th pin, here we have seen this is the output pin. Simply for our understanding purpose, I will write like this. This is 3rd pin, this is 2nd pin, and this is 4th pin, 7th pin, this is the 6th pin. Okay, right. So we have covered mostly all the pins except one pin, that is called pin 8. So what is the purpose of pin 8? So NC, first we have to know the full form of NC. NC is nothing but simply no connection. No connection. We are not going to connect any component or it is not performing any function. That's why we call the 8th pin as no connection or NC pin. We may get a doubt like, if we are not giving any connection or the pin not performing any task, why we have to use that pin? Why can't we skip that pin number 8? That means at left side 1, 2, 3, 4, right side 5, 6, 7. That's all. Those 7 pins only we are using. We are not at all using 8th pin. But why we have why we are connecting this terminal? We are placing this terminal and we are giving some name. That means earlier I told you these kind of ICs has to follow some protocol, that is dual inline package. What is the basic concept of dual inline package? That also I explained earlier. For example, at left side 4 pins are there, right side should be 4 pins are there. Whether we may use it or not, the count we have to maintain. That's why we have fixed this 8th pin as no connection. So that is the pin diagram of IC741 op-amp. Apart from that, few features also here given, that is low power consumption, short circuit protection, offset null voltage capacity. We know about low power consumption, short circuit protection, offset null also just now we have seen, right? So that is one of the main feature of this op-amp 741, IC741. So this is a new topic in this lecture, that is ideal versus practical op-amp. So ideal op-amp, I have placed in the left side, few points I have written. In the right column I have, or second column I have written about practical op-amp. If you observe the symbol, it would be same. It would be same for ideal op-amp as well as for practical op-amp. Symbol we cannot find that much difference. But the thing is, main points or main important parameters we have to know. So if we observe the first point, that is open loop gain. The open loop gain value is infinite for ideal op-amp. Actually, the infinite or 0, these two numbers we can use for ideal devices, not for practical. Infinite practically not possible. Remember, as well as 0 is also not possible. So 0.000001, somewhere we will write 1. That we, for our understanding purpose, we call it as 0. But practically 0 is not available. Like infinity. Okay, infinity is also not available. Some biggest number, we will assume that number as infinite. So ideal op-amp having open loop gain value as infinity. Same, observe the first point across this practical op-amp. Here I have written open loop gain is very high. That means infinite we cannot call practically. So that's why we are calling some very high value will be there. So AOL value of op amp is very, very high, we can say. And the input resistance of operational amplifier is infinite for ideal op amp. Coming to the practical op amp, it is very high. For infinity, we have to write practically very high. It is easy to remember. Try to remember these values, ideal op amp parameter values. Same way practically, we can write if infinite is there, we can write very high. If 0 is there at ideal side, practical side we have to write very low. Like that we have to write. So coming to the third point, output resistance of ideal op amp is 0. If 0 is there at ideal side, what we will write at practical side? We have to write very low, right? That is the difference we have to identify. Later we will see what is this open loop gain, what is this input resistance, what is the output resistance, what is common mode rejection ratio, what is slew rate. In detail we will learn in the coming classes about these parameters. Now just we will try to remember the value what we have to write. Okay, only 5 parameters here I have considered, right? Easy to remember also. One is open loop gain, one is output resistance, one is input resistance, one is common mode rejection ratio, and the last one is the slew rate. So common mode rejection ratio of ideal op amp is infinite, and common mode rejection ratio of practical op amp is very high. Here slew rate of ideal op amp is infinite, and for practical op amp it is very high. So ideal op amp, if we are writing any parameter value as infinite, in practical op amp we have to write it as very high. If we are writing 0 at ideal side, practical side what we have to write? We have to write very low. That's all. So this is about ideal versus practical op amp. We can expect a long answer question, 5 marks question from this concept. Coming to the last topic, that is DC characteristics of op amp. In general, we are having 2 kind of characteristics. One is DC characteristics and second one is AC characteristics. In our curriculum, we are having DC characteristics. So try to remember there are 4 types of DC characteristics will be there. First one is input bias current. Second one is input offset current. Third one is input offset voltage. Fourth one is thermal drift. If you observe the second and third types, total 4 types are there now. So second and third types, we are having this word offset. Offset we have briefly discussed, right? So offset is nothing but, again I am telling, without giving any input, if we are getting any output values from an electronic device, those values are called offset values. That values we have to make as zeros or nullifying those values. Okay, we'll see one by one. First we will see input bias current. So input bias current, here I have considered an op amp. Here 2 base currents are entering. One base current at inverting terminal, minus is inverting terminal, remember, plus indicates non-inverting terminal. So the base value, whatever the base current entering into the negative terminal, we are considering it as IB minus. Whatever the base current value entering into the non-inverting terminal, we are considering it as IB plus. Remember carefully, these 2 values are not equal. Even though whatever the transistors present across these 2 terminals are made up of same kind of material also, these IB minus and IB plus are different values. I will tell you suddenly why I am talking about the transistors. If you observe op amp internally, I will draw a little bigger diagram. This is op amp, right? This is op amp, minus terminal, plus terminal, input terminals, and this is output. You have to remember, internally this op amp consists of around 24 transistors. Number of resistors, capacitors also there. So around 24 transistors will be there present internally of this op amp. Starting, we are having first 2 transistors. Let us assume these 2 are NPN only, made up of same kind of material only, manufactured by same company only, even though IB minus value as well as IB plus value is not equal. That's what I have written here. Okay, due to that we will get some error value. By using some compensation techniques, we can reduce it. What kind of techniques we have to use, those techniques I will discuss in the next class. Next, second one, coming to the second one, that is input offset current. Same, as IB plus, IB minus is having different values. If we found a difference between those two values, we will get the input offset current. Let us assume IB plus is 5 volts. IB minus is also 5 volts. Then there will be no problem. There will be no question of offset. Why? Because 5 minus 5 will become 0 na. So same values, then no problem. But just now I told, even though same kind of transistors we are using, like NPN transistors, both Q1, Q2 we are using, and both made up of same manufacturing company, even though IB minus, IB plus values are different. Due to the difference in the values, we will get these issues, input offset current. Here also same, some compensation technique we have to apply, and we have to make the input offset current value as 0. Here second one is input offset voltage. Here clearly I have explained how can we make that generated voltage value as 0. Let us assume an op-amp, right? Let us assume an op-amp. Here I am grounding the minus terminal. Grounding means 0 volts, that's all. Positive terminal also I have connected to ground. That means across negative terminal or across positive terminal, I am not applying any voltage. So just now we have seen, without applying any input, what will be the output? Output is also 0. V naught equal to 0. Here no problem will be there. Let us assume we are getting a voltage of some 2 volts. V naught equal to 2 volts. Okay. Now what we have to do? We have to make this 2 volts to 0. Otherwise we will get error. Okay. How can we make this 2 volts as 0? See, here clearly I have drawn in this figure 5. Here I have considered one voltage source. See, here I got plus 2 volts. That's why I have connected as minus plus. If I got minus value, I will connect like plus minus. Okay. So I have to adjust this VIOS, input offset voltage, in such a way that it will generate minus 2 volts. What will happen now? Right? Plus 2 we got offset value. Minus 2 volts we are applying across it. Then it will, both will get cancelled and we will get 0 volts. In that way we can reduce the offset voltage. This is one of the compensation technique. So coming to the last type of DC characteristic, that is thermal drift. Okay. So till now we have seen different DC characteristics of op-amp, that is bias current, offset voltage. Let us assume like we have adjusted bias current, offset and offset voltage as zeros. Suddenly the temperature got changed. Then what will happen? These values will also get changed. That is the major concern for this operational amplifier. So I hope you understood. So next, in this paragraph I will clearly explain a circuit carefully nulled or made the offset values as 0. Assume like that. Nulled means we have made the offset values as 0 at a certain temperature. Let us assume that certain temperature as 25 degrees centigrade. Okay. So it means at 25 degrees centigrade, we have made all the offset values as zeros only. Suddenly what will happen? Temperature changes. Changes means maybe increase or maybe decrease. Here we will consider suddenly the temperature changes to some 35 degrees centigrade. What I did here? I have clearly made all the offset values as 0. But the thing is, temperature changed or increased to some 10 degrees centigrade. That means earlier it is 25. Now it is changed to some 35 degrees centigrade. Here what will happen? Here the bias current, whatever till now we have made zeros, offset current, offset voltage, all values will get changed, and this process is called thermal drift. So hope you understood about the concepts ideal versus practical op-amp as well as DC characteristics of op-amp. So that's all for today. In the next class, we will see another topics from the subject IC applications. Right. Thank you.